Welcome back to the deep dive. Today we're embarking on a, well, really crucial journey into a topic that's moving incredibly fast from sci-fi to everyday reality. We're talking about securing agentic applications. Those intelligent AI agents making decisions, taking actions, often on their own, sometimes behind the scenes. And these aren't just your standard chatbots anymore, are they? They're becoming genuine autonomous assistants, capable of complex reasoning, talking to external systems, even like working together. But as we always say, with great power comes, a whole heap of new security challenges. If they act autonomously, what happens if they're, tricked? Or if a tiny flaw leads to huge unintended consequences? That is exactly why we're turning to an incredibly valuable resource for this deep dive, the OWASP Gen AI Security Project Securing Agentic Applications Guide.
Indeed. And this guide, it really is a goldmine. It's packed with practical, actionable insights for anyone involved in designing, developing, deploying these sophisticated systems. What's really great here, I think, is that it's not just theory. It's built for the people actually doing the work, the engineers, the defenders.
Yeah.
It kind of picks up right where other OWASP ASI documents leave off. Their threats and mitigations guide tells you what the risks are. The red teaming guide shows how you might test for them. But this guide, this is the how-to. It gets into the nuts and bolts of building strong defenses right from the start, how to technically implement those mitigations.
So it's truly the how-to manual, making these powerful AI systems safe right from the ground up, translating those theoretical what-ifs into practical steps. And given how specific that sounds, who exactly should be, leaning in and paying close attention to this deep dive?
Yeah, the guide's pretty clear on its audience. It's very focused on the builders and defenders. We're talking software developers, AML engineers, security architects, security engineers, technical leads. Basically, anyone hands-on with building, securing, or assessing these complex workflow and agentic AI apps covers a huge range. Technical security controls, secure architectural patterns, mitigation strategies, the whole development lifecycle, really. Design, build, deploy, operate. It's all in there. And crucially, it dives into the specifics of the key components, LLMs, orchestration, memory, tools. So yeah, if you're working with these systems, this guide, and hopefully our chat today is speaking directly to you.
That covers a lot of ground, doesn't it? It really sounds like a critical resource. Whether you're a startup building a niche agent or a big company integrating AI everywhere, a playbook for making these systems trustworthy. Okay, let's unpack this then. Let's dive into the world of agentic security. So we're starting right at the beginning. The introduction of the OSP guide. Why is this document so vital, like right now? Agentic AI is evolving so fast, moving from labs into the real world. What makes it so crucial?
Well, I think what's particularly striking is its explicit focus on practical and actionable guidance. It's not just another academic paper outlining, what might go wrong. It's designed for the people on the ground, the builders, the defenders. And that practical approach is just crucial because, let's face it, agentic AI introduces fundamentally new security challenges. Think about a traditional software mostly reacts to input. An agent acts on its own initiative. That changes the game. So this guide steps in to provide the how-to. It focuses on concrete technical recommendations developers and architects can actually apply. It builds directly on those other OWASP ASI documents. The threats and mitigations one, for example, it identifies all sorts of threats, prompt injection, memory poisoning, you name it. Then the red teaming guide shows how to simulate attacks. But this guide gives you the engineering blueprint for defense, the detailed technical steps to counter those threats.
Okay. So it really connects the dots. It takes the known threats and gives you the practical toolkit to defend against them. And just to quickly recap for anyone joining, who's the main audience here? Who needs this playbook?
It's squarely aimed at the technical folks. Software developers, AML engineers, security architects, security engineers, tech leads. Basically, if you're hands-on building, securing, or testing these agentic AI systems, this guide and our discussion is absolutely for you. It covers the whole lifecycle design, build, deployment, operations, and digs into the key tech components like LLMs, orchestration, memory tools, the works.
Right. Covers the whole journey from the drawing board to daily operation. Sounds absolutely essential for anyone wanting to make sure modern AI is not just smart, but also safe and, well, responsible. Okay, so we've set the stage. We know why this is important, but how do we actually build these things securely? You can't secure what you don't understand, right? So that brings us to the anatomy of an agent. What are its core building blocks? The guide has a whole section on secure agentic architectures.
Absolutely. And this section, defining key components of agentic architectures, it's foundational, really foundational. It lays out 6 critical key components, KCs, that make up the operational backbone of any agentic system. Let's break them down, starting with maybe the agent's mind. So first up, Generative language models, LLMs. Think of these as the main cognitive engine, the brain basically. They handle understanding, reasoning, planning, generating responses, all that core thinking. But it's not just one monolithic type of LLM. The guide points out several variations. You've got your standard large language models, the big ones like GPT-4 or Claude, general-purpose brains trained on huge data sets, mostly steered via prompt engineering. Then you have multimodal LLMs, MLMs, like GPT-4V or Gemini. These can process more than just text images, audio, maybe even video. Really expands what an agent can do.
Ah, so they have more senses, in a way. Wider input channels.
Kind of, yeah. And importantly, there are also small language models, SLMs. These are much more specialized, efficient for specific tasks, fewer parameters, smaller context windows, and finally, fine-tuned models. These are LLMs or MLMs that get extra training on specific data sets to specialize them or give them personas, or, crucially for security, maybe fine-tuned to reduce answering out-of-scope questions.
Got it. So it's not just one giant brain, but a whole spectrum of cognitive engines. Some specialized, some multi-talented, some tuned for specific jobs. Makes sense. What about how these brains are controlled, how the agent's actions are, orchestrated?
All right, that takes us to KC2, orchestration, control flow mechanisms. This dictates the agent's overall behavior, how information flows, how decisions get made. It's like the agent's nervous system directing its actions. The guide outlines a few main patterns here. You've got simple workflows, which are basically structured, predefined sequences of tasks, like a script the agent follows. Then there's hierarchical planning. This is more complex. You have a central orchestrator agent that breaks down big tasks, routes them to specialized sub-agents, monitors them, like an AI project manager. And finally, multi-agent collaboration. Here, multiple agents work together more like peers, communicating, coordinating, without a strict hierarchy. Good for really complex tasks needing diverse skills.
Okay, that clarifies how the different parts interact. The nervous system analogy works well. Then there's KC3, reasoning planning paradigm. This sounds like how the agent actually figures out what to do. It's strategic thinking.
Yep.
Exactly. The reasoning planning paradigm is what enables agents to tackle complex, multi-step problems. It's how they break down goals into smaller steps and figure out the best sequence of actions. How they think strategically. Key paradigms mentioned include structured planning execution, where tasks become formal plans with defined actions. There's REACT, reason plus act, which is more dynamic. It interleaves reasoning steps with actions, updating its thinking based on what happens. Chain of thought, COT, which you've probably heard of, prompting the LLM to think step by step before giving an answer, makes reasoning more transparent. And tree of thoughts, TEA, which is like COTI on steroids. It explores multiple reasoning paths at once, looks ahead, evaluates options, really sophisticated strategizing.
Fascinating. So it's about how the AI strategizes, not just responds. What about its memory? How does it keep track of things?
That's KC4. Memory modules, absolutely critical. These let agents retain information. Short-term memory for the immediate context, long-term memory for past interactions, knowledge. This is what enables coherent conversations and personalization over time. A key concept the guide raises is context sensitivity, basically, classifying information to reduce the risk of exposing stuff it shouldn't. For long-term memory, retrieval augmented generation, RG, often using a vector database, is pretty common. Now, the guide details 6 types of memory, and this is important. They escalate in terms of shared access and therefore potential risk. The more widely memory is shared across agents, across sessions, across users, the higher the security risk if it gets compromised. It's like going from your private diary to a public wiki. If memory shared across multiple agents and users gets poisoned, boom, you could have widespread data leakage or manipulation. The potential blast radius is huge.
That can take perfect sense. More sharing equals more risk. Okay, so the agent can think, plan, remember. But how does it actually do things in the world? You called them the arms and legs earlier.
Right, that brings us to KC5, tool integration frameworks. This is how agents go beyond just text, how they use external tools, APIs, functions, databases to interact with other systems or the real world. The framework manages picking the right tool, using it correctly. The guide mentions different types, flexible libraries, SDKs like LangChain. Gives you lots of control, but needs more coding effort. Managed platform services like Amazon Bedrock agents. Vendor handles infrastructure, simplifies setup, often low code, trades flexibility for speed. And managed APIs like OpenAI's Assistance API, vendor hosted, focuses on the API, manages state and complexity behind the scenes.
So tools are the agent's interface to the world. It's arms and legs. And where do these arms and legs actually operate? What environment are they interacting with?
That's KC6, operational environment, agencies. This is where the rubber meets the road. Agents interface with external environments through those tools. The guide details different levels of capability here, each with its own risks. Some really stand out in terms of potential danger, like code execution. This capability means the agent can run code. It might just generate parameters for a predefined function, or it could run arbitrary code generated by the LLM itself.
Whoa, arbitrary code execution. That sounds incredibly risky.
It is extremely high risk. A compromised agent could execute anything. And then there's operating critical systems, like SCADA controls in industrial settings. This is the absolute highest risk category. An agent messing with industrial controls. Unauthorized operations could lead to catastrophic physical failures. Think power grids, manufacturing plants. The real-world impact is immense.
Wow. Yeah, that really drives home the stakes, from changing my smart lights to potentially impacting critical infrastructure. Okay, so with all these components interacting, what does this mean for attacks? Where are the weak spots?
That's the crucial question, isn't it? What are the attack surfaces? The guide then dives into attack surface analysis. This maps specific threats using the T-codes from the ASI threats and mitigation stock to each key component. It helps pinpoint vulnerabilities. For instance, with the LLMs, KC1, the brain, you worry about threats like cascading hallucinations, T5, where small errors amplify and attempt breaking, T6, tricking the AI. For orchestration, KC2, it's also T6, manipulating the workflow, but also things like communication poisoning, T12, in multi-agent setups, and rogue agents, T13. Memory modules, KC4, are vulnerable to memory poisoning, T1, injecting bad data and privilege compromise, T3, through context leakage. Tool integration, KC5, is susceptible to tool misuse, T2, and critically unexpected remote code execution, T11. And the operational environment, KC6, well, it faces risks across the board, depending on the capability, tool misuse, TDL, privilege compromise, T3, resource overload, T4, RCE, T11.
Okay, now this is where it gets really interesting and maybe a little scary. It's so clear that a weakness in one spot, say a poisoned memory entry, can cascade. It can mess up the reasoning, lead to tool misuse, and cause real harm in the operational environment. So given this complex web of interactions and potential failure points, what's the big picture for building secure systems? How do we approach this holistically?
The guide really hammers this home. Building secure agentic systems demands a holistic approach. Security can't be an afterthought. It has to be baked into the architecture itself right from the start. This leads to the concept of secure architecture patterns. These are essentially blueprints for how components should interact securely and resiliently. There are core patterns that act as fundamental building blocks, like the tool use pattern, which defines how agents safely use external tools, requires clear definitions, secure selection logic. The reflection pattern lets agents review their actions and self-correct, good for improvement, but needs safeguards against malicious self-correction. And the retrieval augmented generation, RAG pattern, enhancing LLMs with external knowledge. Makes them smarter, but you have to secure that knowledge base against poisoning or data leaks. Beyond these core patterns, the guide outlines three main architectural types. The sequential agent architecture, simple, linear workflow, single agent. The most basic setup, hierarchical agent architecture, role-based multi-agent systems, more complex. A central orchestrator manages specialized sub-agents. That orchestrator is a key security point. And collaborative agent swarm, distributed agent mesh. Multiple peer agents, no strict hierarchy. Decentralized, which brings unique trusts and communication security challenges.
Those diagrams in the guide are really helpful for visualizing these. You can see the flow change from simple linear to complex distributed networks. It feels like we're scaling up complexity. And you mentioned frameworks earlier. There are tools to help build these different architectures, right? So we don't have to start from scratch every time.
Absolutely. Section 2.3 covers frameworks. Loads of them exist. LangChain, AutoGPT, Crew AI, Amazon Bedrock agents, Microsoft Semantic Kernel. The list goes on. They offer pre-built components, abstractions for state management, tool integration, orchestration. Definitely accelerates development. However, the guide gives a really important warning here. Your choice of framework significantly impacts your security posture. It affects how easily you can implement controls and what your attack surface looks like. And there's this key trade-off, customization versus abstraction. Frameworks are great for getting started, proof of concepts. But in production, they create dependencies. If you heavily modify a framework and then a critical security patch comes out for that framework, updating can become a nightmare. Your custom code might break. It can lead to fragility right when you need to be agile. That's a huge consideration.
That's a really practical warning. Convenience now might mean pain later if you're not careful about dependencies and updates. So understanding the framework's internals is key, not just using it as a black box.
Exactly. You need to know how it implements those underlying key components and architectural patterns to assess the security implications properly.
Okay, components, architectures, frameworks. It's a lot of theory. Can we see it in action? Walk us through that case study you mentioned.
Yeah, the guide uses a great example, a multi-agent copilot application. Very common use case. It implements a hierarchical planning architecture, KC2.2. So there's a central orchestrator agent. It takes user requests, schedule a meeting, summarize my emails, breaks them down using its LLM brain, KC 1.1, and structured planning, KC 3.1, and routes tasks to specialized agents. It uses cross-agent session memory, KC 4.22, meaning memory is shared between the orchestrator and the specialists within a single user session. This immediately flags the need for context sensitivity, careful handling of what info is shared to prevent leaks. Then you have specialized agents, one for calendar, one for email, one for Slack, one for Drive. Each has a specific job and uses limited API access, KC 6.1.1. This means they interact with services like Google Calendar via predefined API calls. The agent's LLM might just generate the parameters for the call, like meeting time or email subject, not the whole API request structure itself.
Okay, so even this helpful copilot, designed with what sounds like relatively safe, limited API access, still has risks. It really shows security needs to be proactive. What threats does the guide highlight for this copilot?
Even with that limited access, it's definitely not risk-free. Tool misuse, T2, is a big one. An attacker could craft a sneaky prompt to make the LLM generate malicious parameters for a legitimate API call. Maybe tricking the email agent into sending an email with a dodgy subject that exploits a vulnerability in the mail client. Intent breaking and goal manipulation, T6 is another. Using prompt injection to manipulate the orchestrator or a specialist agent's LLM towards a harmful goal, even within those API constraints, like getting the calendar agent to schedule a meeting designed to phish someone. And identity spoofing, T9. If the LLM generates parameters that include user IDs, an attacker might try to manipulate those to make an action appear to come from someone else. Imagine tricking the Slack agent into posting a message as the CEO.
Wow, okay, so even simple parameter generation can be a vector. This really underscores why we need detailed guidelines. Which brings us to the next big section. Right. So we've defined the parts, seen how they fit together, looked at a case study. Now, what are the actual agentic developer security guidelines? It feels like security has to be woven in from the very beginning, right? Not just slapped on at the end.
Precisely. The guide is really strong on this. It emphasizes a lifecycle approach. Security isn't a phase. It's integrated from initial design all the way through deployment and ongoing operations. It has to be a foundational principle. And that's because agentic AI introduces these fundamentally new security surfaces that we just haven't had to deal with quite this way before in traditional software. Think about persistent memory. It creates risks of context poisoning, data staying around when it shouldn't. Or autonomous planning that opens doors to misaligned goals, agents getting stuck in loops, unpredictable behavior. These unique AI risks demand new considerations right from the design phase. It's not just traditional threat modeling. It's defining safe failure states, mapping integration boundaries carefully, specifying memory access policies up front, and ensuring human-in-the-loop (HITL) safeguards are designed and where needed.
That makes total sense. You have to anticipate these unique AI failure modes from day one. Okay, so let's start with the secure design and development phase. What are the key activities here?
Okay, in secure design and development, several critical areas pop out. First, threat modeling for agentic systems. It builds on traditional threat modeling, but adds these AI-specific concerns, like defining those safe failure states. What does the agent do if it gets confused or can't complete its task safely? How does it fail gracefully? Charting integration boundaries is key, and specifying memory access policies, who can read, write what, when. Plus, integrating HIPL checks at critical points. Another huge one is system prompt engineering and hardening. The system prompt is like the agent's core programming, its constitution. It defines its purpose, capabilities, limitations. Hardening this is vital. Practical approaches include setting clear boundaries and safeguards, explicitly stating DOs and don'ts, forbidden topics. The guide leans towards an allow-list approach, define what it can do, deny everything else implicitly. Making prompts robust against injection is paramount. Using clear delimiters like XML tags to separate instructions from user input, instructing the model itself to be wary of attempts to override its instructions, and minimal and focused fine-tuning. Fine-tuning can help enforce security, but it can also accidentally overwrite the model's built-in safety training. So it needs really careful testing and benchmarking.
So we're essentially programming the AI's core directives securely, like writing its operational manual and making sure it can't easily be tricked into ignoring it. What about the actual code developers write?
Right, secure coding practices. The guide adapts standard principles for AI agent development. The fundamentals still apply, but with an AI twist. Input validation is crucial, but now it includes validating user prompts, API responses, data retrieved from memory, basically all inputs. Allow listing is preferred. Secure key management, no hard-coding secrets, obviously. Use proper secrets management services, never log secrets. Least privilege every component runs with the absolute minimum permissions it needs. Content moderation integration needs to be planned early. How will you detect and filter harmful content, both coming into the agent and going out? What tools will you use? How will moderation results trigger actions? And human-in-the-loop, HITL, design. This is so important. Identifying where human oversight is absolutely necessary before high-impact actions, sending emails, changing databases, executing code, spending money. You need clear workflows for review, user-friendly interfaces, and logging of human decisions. And, critically, strong rate limiting on HITL prompts to stop attackers overwhelming the human reviewer.
That HITL part seems especially vital for building trust and ensuring safety, particularly with those high-stakes actions that have real financial or operational consequences. Okay, what about managing information over time, securing the agent's memory?
Yes, memory security design. This is about protecting both short-term session and long-term memory, like vector databases, from unauthorized access, tampering, and data leakage. Memory poisoning is a major threat vector. Key controls involve robust access control, IAM roles, API keys, database permissions based on least privilege. Proactively stripping dangerous tokens from past messages or memory entries, things like ignore previous instructions to foil injection attempts, standard encryption for data at rest and in transit, input validation for memory set to sanitize data before it gets stored, and PII handling, designing mechanisms to detect and redact or anonymize personally identifiable information before it hits the memory is absolutely critical for privacy compliance. Related to this is input-output validation and sanitization design, ensuring the integrity and safety of all data flowing into and out of the agent and its tools. This involves applying AI guardrails as automated security filters on both inputs and outputs, using robust input sanitization and escaping, especially stripping special tokens before injecting user input into prompts. Enforcing schema enforcement for tool arguments and outputs, using something like JSON with strict parsing really helps. And planning your output sanitization strategy, how will you neutralize potentially harmful content, like scripts, in LLM outputs before rendering them or passing them on? Using secure rendering methods in UIs is key. Finally, in the design phase, authorization and authentication, making sure the agent system itself is properly authenticated and authorized to perform actions or read data, often involving identity providers and maybe even decentralized identifiers, DIDs for agents.
Okay, that's a lot to consider just in the design and development phase. So assuming we've done all that diligently, how do we ensure the build and deployment process itself is secure? How do we get the agent ready for the real world safely?
Right, that takes us to the secure build and deployment phase. This isn't just about compiling code, it's about establishing robust, adaptive development lifecycles tailored for agentic systems. Deployment pipelines need to be able to snapshot configurations, log audit trails, embed signed constraints on tool usage. Release protocols need rollback capabilities and runtime enforcement of boundaries. Key practices here include static analysis, SAST, and dependency scanning, SCA. Integrating tools like Bandit or Snyk directly into your CI/CD pipeline to catch vulnerabilities in your code and third-party libraries before they ever get deployed. Environment hardening and sandboxing. This is absolutely crucial for agents. You need to isolate the agent's execution environment to limit the blast radius if it does get compromised. This means running agent code, especially any LLM-generated code, in tightly controlled sandboxes, OS-level containers like Docker, maybe even lightweight VMs like Firecracker, configured with strict file system and network restrictions. Least privilege applies here too. Secure configuration management. Managing secrets, API keys securely. Using dedicated systems like AWS Secrets Manager or HashiCorp Vault. No secrets in code. No secreting in FIG files checked into Git. Pre-deployment testing. Actively trying to break the agent before it goes live. This includes fuzzing the prompt interface with tools like PromptFoo or Pirate, API fuzzing, and targeted penetration testing. Implementing runtime security with memory isolation. Using architectures like Google's Camel to separate the agent's control flow generation from potentially untrusted data processing. This provides defense in depth, even if the LLM itself is vulnerable. And using just-in-time JIT access and ephemeral credentials, granting permissions only when needed for the shortest time possible. Using short-lived tokens significantly reduces the window for misuse if credentials leak.
Okay, makes sense. Design secure, build secure, deploy secure. We've covered getting the agent ready. What happens once it's live? Running in the wild? How do we keep it secure during operation?
That's the domain of the secure operations and runtime phase. And this is all about continuous vigilance and adaptation. Live agentic systems need monitoring that goes way beyond just checking if they're up or down. Runtime observability has to capture decisions, plan evolution, memory access, tool interactions. Any behavioral drift, deviations from expected plans, weird tool usage needs to trigger alerts or safeguards immediately. Key practices include continuous monitoring and anomaly detection, real-time detection of malicious activity, policy violations, or just strange behavior. This means scanning LLM inputs/outputs for jailbreaks, monitoring tool calls for unusual frequency or parameters, watching memory updates for signs of poisoning, analyzing communication patterns in multi-agent systems, and feeding all these signals into your scene security information and event management system. Then you need runtime guardrails and automated moderation. These are your dynamic fences, enforcing policies while the agent runs, real-time checks on inputs/outputs to block or sanitize harmful content. Careful placement of these guardrails is important. Placing them within the application or agent code often gives better visibility than just at the network edge. Implementing memory TTL, time to live, to automatically purge old data. And ongoing memory sanitization and PII redaction using tools like Microsoft Presidio SDK to clean sensitive info before it gets stored persistently.
So, constant vigilance, automated fences, watching the agent's every move. Makes sense. What about after the fact? If something does go wrong, how do we figure out what happened? Forensics.
Exactly. Logging, auditing, and traceability. This is critical. The guide points out, quite rightly, that agents will fail or be involved in incidents eventually. And crucially, LLM providers usually don't keep detailed logs of interactions. That responsibility falls squarely on whoever deploys the agent. So you need comprehensive logging, record agent raising steps, plans generated, tool calls made, parameters used, HITL interactions, everything needed for debugging, security analysis, and compliance. Structured logging, like JSON and trace IDs, are essential for piecing things together. And a huge point here is operational security, OPSEC, in logging. You absolutely must protect the logs themselves. Use secure immutable storage, apply least privilege access to logs, and most importantly, never log sensitive information directly. Source codes, session IDs, API keys, PII, passwords, financial data. All of it needs to be removed, masked, hashed, or encrypted before it hits the log files. Logs can become a treasure trove for attackers if you're not careful. The guide also covers incident response planning, having a plan before an incident happens. Defining what constitutes an incident, outlining steps for containment, analysis, remediation, assigning roles, testing the plan, and finally, AI bot mitigation and controls. Recognizing that AI agents are the next evolution of bots. Verifiable agent identity is crucial to prevent spoofing. The guide advocates for a multi-factor identity bundle, stable network metadata, cryptographic request signing, maybe an agent name service, ANS, for standardized identity lookup. This allows systems to verify who they're talking to.
Wow, that is incredibly detailed. It covers the entire life cycle, from the initial idea right down to managing logs and agent identities in production. It really emphasizes that multi-layered defense approach. Okay, so we've gone through the general developer guidelines covering the whole life cycle, but you mentioned earlier that the type of agent system matters. Does the guide offer specific enhanced security actions based on the architecture? Does a simple single agent need different defenses than, say, a complex swarm?
That's an excellent point, and yes, the guide does exactly that. It segments enhanced security actions by architecture, recognizing that while the core principles apply everywhere, the emphasis and specific controls change depending on the system's complexity and how the agents interact. So first, for single agent systems. Even though they're the simplest, they still need a comprehensive security strategy. You can't skimp just because it's only one agent. This means strong authentication and authorization, things like OAuth 2.0 with PKCE, least privilege access tokens, maybe managed identities if you're in the cloud, robust data protection, encrypting sensitive data in transit and at rest, using data loss prevention, DLP tools if needed, applying data minimization principles. Rigorous code security automated testing, SS, DEST, SEA, and CI/CD, thorough code reviews, constantly monitoring dependencies, continuous monitoring and incident response detailed logging, including maybe a log chain of thought for sensitive operations, real-time anomaly detection, alerts, incident response plans, and definitely having emergency kill switches, and comprehensive prompt security input validation, output filtering, hardening those system prompts, sanitizing inputs to prevent injection. It's basically adapting best practices from traditional AppSec for the AI context.
Right, so even the simplest agent needs the full treatment. Makes sense. What about when you have multiple agents working together, especially with that central orchestrator model we discussed? That sounds like it adds new wrinkles.
It absolutely does. That brings us to multi-agent systems with central orchestrator. These systems reuse many of the single-agent controls, naturally, but they add specific considerations because of that central coordinator and the inter-agent communication. orchestrator security becomes absolutely paramount. That orchestrator is coordinating everything, so it's a potential single point of failure and a high-value target. You have to harden its API vigorously, authentication, rate limiting, input validation, detailed logging. You need to protect against control flow hijacking, where an attacker manipulates one agent to trick the orchestrator. This involves validating agent responses and maybe using integrity checks, and mitigating the confused deputy problem, preventing the orchestrator from being tricked into misusing its legitimate authority. Interagent communication is another critical area. How do agents talk to each other securely? This requires secure protocols, ideally mutual TLS, MTLS, for two-way authentication between agents. Verifying the identity of each agent involved in the communication is key, maybe using certificates or tokens. Using secure message queues can help. Deploying policy enforcement points, PEPs, as security checkpoints in the communication channels is also recommended. And applying trust boundaries using zero trust principles, never trust, always verify, even between your own agents. Implementing network segmentation and isolating agents using containers.
Yeah, connecting that back. If the orchestrator is the conductor, you need to protect the conductor and ensure that musicians are only talking to each other through secure channels and that they actually are the musicians they claim to be. Okay, what about those swarm systems, the ones without a central leader, where agents are peers? That sounds like managing trust gets even harder.
That's absolutely right. Multi-agent systems with swarm architecture, these are the most decentralized, and they pose unique security challenges precisely because there's no central authority managing trust or communication. They still need the foundational controls from single and hierarchical systems, of course. But a critical difference is the need to explicitly identify trusted agents and permissible actions outside the agentic flow itself. You can't rely on an orchestrator to gatekeep. This is where decentralized identity and trust becomes not just important, but really the cornerstone of security for swarms. With no central authority, you need other ways to establish trust. Decentralized identifiers and BIDs are key here. This is a W3C standard allowing agents to have self-sovereign, verifiable identities that don't rely on a central registry. Think of it as a digital passport for agents. Verifiable credentials, VCs, built on DIDs. Agents can use VCs to prove specific attributes, capabilities, or permissions to other agents, again, in a verifiable, decentralized way. And potentially decentralized replication systems, where agents build up trust scores based on past behavior, helping other agents decide whether to collaborate with them.
This raises a really important question, doesn't it? If there's no central orchestrator, how do you manage and secure all those individual identities and interactions effectively? DIDs and VCs sound like the right direction, but it feels like a whole new frontier for security infrastructure.
It really is. And that's precisely why these decentralized identity mechanisms are so crucial for swarm architectures. They enable that peer-to-peer authentication, clear provenance tracking, and granular access control that you absolutely need when there's no central point of control. Finally, the guide wraps this section with cross-architecture security considerations, things that apply universally, regardless of the pattern. Secure API design for agent communication, continuous security testing, robust security monitoring and threat detection, and having secure agent update and maintenance processes.
What a comprehensive roadmap indeed. It really drives home that security needs to be tailored to the specific architecture and interaction model. Okay, we talked earlier about KC6, the operational environment, being a major attack surface, the agent's arms and legs interacting with the real world. Now let's dig deeper into the specific controls needed for each type of operational capability. This is where the agent actually does things, where the risks become very tangible.
Exactly. These key operational capabilities are where agents touch external systems, and each interaction method brings unique risks. The guide provides specific necessary controls for each one. Let's start with KC 6.1 API access is super common. Agents calling APIs. Core threats. Unauthorized data access, T3, API abuse leading to DOS or big bills, T4, T2, compromised API keys, T3, T9. Controls focus on enforcing least privilege. Using fine-grained OE scopes, limited API keys. Think specific permissions in Okta, Auth, or granular AWS API Gateway or Cloud IAM roles. Using allowed deny lists for APIs. Clearly defining which domains or specific URLs the agent is allowed to call. Authenticating those target URLs. Maybe using outbound proxies or network policies. And a key recommendation: prefer API templates over complete LLM-generated API calls. This is a big one for reducing risk. Have the LLM fill in parameters in a predefined safe template rather than letting it generate the entire API call structure, which could be malformed or malicious. Next, KC 6.2 code execution. As we said, potentially the highest risk.
Threats are arbitrary code execution, RCE T11, T3. Code injection, T11, T2, DOS T4. Info leakage, T6. Controls here have to be stringent. Mandatory sandboxing is non-negotiable. OS-level isolation, containers, VMs, WebAssembly, whatever it takes to run that code in the cage. Static analysis on agent-generated code. Use tools like Bandit or SemGrep to scan any code the agent generates before it runs. Enforce resource limitations, strict CPU, memory, network, and execution time limits within the sandbox.
Yeah, that capability running code just sounds like the ultimate power and therefore the ultimate risk. If an agent can run arbitrary code, it can potentially do anything the sandbox allows. The controls need to be rock solid.
Absolutely. Very high risk. Okay, next, KC 6.3 database execution. Queries and RAG access. Threats here are classic SQL injection T2, unauthorized data access or modification T3, and for RD, data poisoning in the vector database T1, T5, T3. Controls include using managed vector databases with access controls, restricting who can ingest data, applying data classification labels, implementing query safety measures. This is basic database security, but critical here. Explicitly use parameterized queries or ORMs. Never ever build SQL queries by concatenating strings with user input. That's just asking for SQL injection. Use least privileged database accounts, maybe read-only access, limited tables. Filter dangerous SQL keywords. Validate all user inputs. For ARGI-specific controls, filter retrieved content for sensitive info after retrieval, verify content before embedding it into the vector DB, and rate limit retrieval operations. Then there's KC 6.4 web use, agents browsing the web, threats interacting with malicious web content, XSS, exploits T11, info leakage T6, phishing T7, server-side request forgery, SSRF T2, T3, accessing the user's browser data T3. Controls involve sandboxing browser components tightly, running the browser in a controlled environment, maybe without extensions. URL security is key. Filtering URLs with allow lists. Using secure web gateways, SWG, DLP solutions, reputation checks, proper TLS verification, blocking open redirects. Applying protective measures like network segmentation to mitigate SSRF impact, throttling web access, restricting downloadable file types, sanitizing fetched content.
Agents browsing the internet? Yeah, what could possibly go wrong, right? Sounds like you need some very, very strong fences around that capability.
Indeed. Next, KC 6.5, controlling PC operations, file system OS commands. Another high-impact one. Threats, unauthorized file access modification, T3. Arbitrary OS command execution, T11, T3, T2. Potential for lateral movement, T3. Controls again emphasize strict isolation, OS-level sandboxing, running the agent as a restricted user, dedicated containers or VMs, implementing access controls, strict allowed nihilist for permitted OS operations and file paths, maybe using virtual file system interfaces. Intercepting OS command calls for validation, limiting accumulation of sensitive data within the sandbox that should be ephemeral if possible, enhancing monitoring and potentially requiring HITL for critical OS operations. And finally, KC 6.6 operating critical systems, or SCADA controls. The highest stakes, threats, catastrophic physical outcomes T2, T3, T6, T7, malicious control injection T2, T6, false data leading to bad decisions T1, T5. Controls here are maximal. Apply maximal isolation, think air-gapped or highly segmented networks, plus physical security. Enforce multi-factor authentication, MFA for sensitive actions, but critically this must be via an external flow. The agent itself should not mediate the MFA process, as it could be compromised. Mandatory human-in-the-loop, HITL, for every critical action. And the guide makes a good point. The HITL prompt needs to be clear and succinct to keep the human reviewer engaged. Too much noise leads to rubber stamping. Implementing safety mechanisms. Default agent permissions to read only. Anomaly detection tuned for system safety limits. Adhering to industrial control standards like IEC 62443. Physical interlocks, emergency overrides.
That last one really drives home the potential impact. Compromise here isn't just data loss, it's physical disruption, potentially harm. It really underscores the need for that human oversight and making sure the human isn't overwhelmed or deceived. That's a perfect segue. We've talked a lot about securing the agent itself, its code, its runtime. But this next section, Agentic AI and the supply chain, seems to argue that security extends far beyond that. It's about trusting everything that goes into and around your agent. What are the key takeaways here?
Yeah, this is a crucial perspective and one that's often overlooked. The supply chain for agentic AI is incredibly complex. It's not just the code libraries you use, it's the base LLM models, the data they were trained on, the platforms they run on, the tools they discover. It's the whole ecosystem. The guide breaks it down into a few key areas. First, code security in the supply chain context. For third-party libraries and frameworks, standard software supply chain security practices apply. That means robust SCA scanning, using log files for dependencies, generating SBOMs, software bill of materials, table stakes, really. But then there's LLM agent-generated code. This is unique. The guide stresses mandating sandboxing for any code generated or run by an agent, linking back to section 3.2.3. Validating packages before allowing generated code to install or run them. using HITL for high-risk code execution, and checking licenses and provenance of libraries before installation. Next, environments and development. This is about the integrity of the whole development and deployment pipeline. Regarding the LLM logic system itself, try to use the same LLM versions in dev test as in production for consistency and reliability. Ensure the provenance of the LLMs you use. If you pull a model from a Hugging Face, verify its hash, check the contributors. Scan the models themselves for known vulnerabilities if possible. Regarding the LLM logic system itself, use version control not just for your code, but also for the LLMs, and importantly, for your prompts and instructions. This increases reliability and auditability. And a critical point on permission management. Do not give agents access to the code repositories or data sources that build or deploy them. That's a huge risk. Permissions to infrastructure or data sources should always be managed outside the agent's runtime environment. Finally, agent and tool discovery. How do agents find and trust other agents or external tools, especially in dynamic or multi-agent systems? Using things like agent cards or manifest to describe an agent's capabilities and identity. Minimizing trust with unvalidated agents. Employing DIDs for verifiable agent identity, and managing local versus remote agent registries, using logical or network barriers to prevent agents from accidentally discovering or interacting with agents or tools they shouldn't, classifying agents' data and actions as private or public, maybe using certificate pinning to ensure agents only talk to approved registries.
So it really is about extending that zero trust philosophy to absolutely every component and interaction in the agent's lifecycle, verifying the origin and integrity of the models, the code, the tools, the agents themselves. It's a much broader view of security. Okay, so we've designed securely, built securely, considered the whole supply chain, but how do we know it's actually secure? This next section on assuring agentic applications seems to be about exactly that, proving the security measures actually work in practice. How do we get that assurance?
Yeah, exactly. Assurance is about moving beyond just implementing controls to actively validating their effectiveness. It involves dynamic adversarial testing to uncover weaknesses that static analysis or design reviews might miss. The guide highlights two main pillars here: red teaming and behavioral testing. First, red teaming agentic applications. This is where you simulate real-world attacks to find vulnerabilities before the bad guys do. For agentic AI, red teaming needs to go beyond just standard prompt injection. It needs to look at things like privilege escalation through misused tools, memory poisoning attacks, manipulating the agent's planning process. The OWASP ASI Red Teaming Guide provides a methodology for this, emphasizing a holistic view model review, implementation testing, infrastructure checks, runtime behavior analysis, and specialized tools are emerging specifically for agentic AI red teaming. Tools like Agent Dojo for dynamic evaluation, Agent Fence for prompt injection and role confusion, Agent Security Bench, ASB, covering prompt injection, memory poisoning, and even plan of thought backdoors.
So this is where the ethical hackers come in, specifically trained to think like an adversary targeting AI agents. It's fascinating that we already have specialized frameworks just for red teaming these systems. What about the other pillar, behavioral testing?
Right, behavioral testing for agentic applications. This focuses less on finding specific vulnerabilities and more on evaluating how the agent actually behaves across different situations. Does it act consistently, safely? Does it achieve its goals without causing unintended harm? It aims to uncover hidden problems like unexpected emergent behaviors, logical flaws, or alignment issues where the agent pursues harmful goals. This often involves using benchmarks, standardized text to evaluate performance. The guide mentions examples like Agent Bench, evaluating task solving across different domains, HELM for broad evaluation including fairness, bias, toxicity, and WebArena, testing agents in realistic web environments. The guide provides a useful step-by-step process for selecting the right security benchmark based on your specific objectives and threat landscape. It stresses evaluating benchmarks for their relevance, coverage, and ability to provide actionable insights. And a key part of behavioral testing is explainability audits, trying to understand why the agent is doing what it's doing. Using techniques like chain of thought logging, having HITL at critical points, maybe using traditional XAI methods like SHAP or LIME where applicable, and logging agent-to-agent negotiations or tool interactions.
What really strikes me here is that shift in focus. It's not just did the agent complete the task, it's how did it complete it? Was it safe? Was its reasoning sound? Can we understand and trust its process? Homely. It's a much deeper level of assurance needed for autonomous systems. Okay, we're getting towards the end of the life cycle. This section is all about the practicalities of secure agentic deployments, taking these complex, assured systems and getting them into the real world safely and reliably. What are the key principles for that final push into production?
Yeah, deploying these agents isn't trivial. It requires rigorous security that goes beyond just the model's inherent safety features. The actual deployment infrastructure and processes are critical. The guide highlights several key practices. Secure pipelines and checks for rogue agents. Your CI/CD pipeline needs to be locked down. Incorporate automated vulnerability scanning, SAST, SCA, daylist, static analysis focused specifically on insecure tool usage patterns, dynamic testing looking for prompt injection or goal deviation before deploying. Consider code signing and provenance tracking, maybe even manual security reviews for high-risk agents. Role containerization or function as a service, FAS. Isolate agents. Each agent or even distinct roles within an agent should run in its own strongly isolated environment. Docker containers managed by Kubernetes or serverless functions like AWS Lambda or Google Cloud Functions. This enforces strict resource limits, network segmentation, ephemeral execution, reinforcing least privilege at the infrastructure level. Limits the blast radius if one agent gets comped. API access control, rate limits, and API gateways. Don't let agents call tools or external APIs directly. Mediate all invocations through an API gateway or a dedicated agent gateway. This is where you enforce strict authentication, authorization, who can call what, and granular rate limiting, preventing DOS and controlling costs. It's also a vital logging and auditing point, alerting on anomalous behavior. You need continuous monitoring that baselines normal behavior, typical tool usage, resource consumption, communication patterns, and triggers alerts on significant deviations. Unexpected tool use, sudden goal shifts, weird data access patterns, these need immediate attention. Human oversight in high-stakes environments. We've touched on this, but it's crucial at deployment. For critical decisions or actions with significant consequences, finance, healthcare, critical infrastructure, robust HITL workflows are non-negotiable. Sometimes even human over-the-loop, continuous supervision. The EU AI Act's high-risk categories can offer guidance here. Managing non-human identities. Treat agent identities like user identities. Each agent instance needs a distinct, securely managed identity, like a service account or workload identity. This means secure provisioning, robust credential management, rotation, secrets managers, clear ownership, and reliable deprovisioning when an agent is retired.
This really sounds like applying mature DevOps and SecOps principles, but adapting them very specifically for the unique characteristics and risks of AI agents, treating them almost like autonomous employees with their own identities and permissions that need careful management. Okay, we've reached the final section, runtime hardening. The agent is designed, built, tested, deployed. Now it's running live. This seems to be about the nitty-gritty technical controls to protect it while it's actually doing its job in its operational environment. How do we secure that?
Exactly. This is about defense in depth at the lowest levels, protecting the agent while it's executing. It combines traditional infrastructure security with controls specifically tailored for agentic runtimes. The guide breaks this down systematically. 9.1, harden the virtual machine, base level. Start with the foundation. The host VM or container host needs to be secure. Use minimal base images like distroless or Alpine Linux. Enable secure boot. Use TPM-backed disk encryption. Disable unnecessary services. Apply strict firewall rules. Patch regularly. Isolate it, network-wise, private subnets. Controlled communication via service meshes or gateways. No direct internet access unless absolutely required. Basic OS hardening, essential. 9.2 contain the agented runtime. Now focus inside the VM sandbox. The agent processes themselves. Run each agent or maybe even each tool invocation in its own restricted namespace or lightweight container like gvisor, Firecracker, or Docker in VM. Use mandatory access controls like a Parmer, Linux, or SACOMP profiles to restrict what system calls the agent can make. Limit file system access. Inject ephemeral storage for sensitive operations. Scoped capabilities. Implement a capability control layer. Agents should only be able to use tools they've explicitly been granted permission for, maybe using capability tokens for a session. Use wrappers, like JSON RPC, around tool calls to enforce these boundaries dynamically.
And this is really getting into the weeds, the highly technical, granular controls for locking down the agent's immediate execution environment, making sure it stays in its designated playpen.
Precisely. And it continues with 9.3, secure the agent's memory, tools, and context. Protect data while it's being processed. Encrypt in memory state where feasible, though this can be complex. Automatically clear memory when a session ends. Use VM hooks or other mechanisms to flush memory or rotate encryption keys periodically. Implement runtime guards specifically for tool calls. Validate inputs-outputs at the moment of invocation. Scan for prompt injection before passing data to the tool. Use policy engines like OPA, Open Policy Agent, to dynamically gate access based on context. AG, only the finance agent can call the billing API. 9.4 Observability plus forensics. Log everything an agent does. Tool use. Messages sent received. Memory reads writes. Logs need timestamps, agent IDs, session IDs, maybe payload hashes or signature fingerprints for integrity. Store these logs securely, ideally with forward integrity. Append only, maybe Merkle proofs or sign logs. Complement this with the behavioral anomaly detection at runtime using policy engines or even specialized LLM anomaly detectors to spot unusual tool sequences, weird communication patterns, or sudden memory usage spikes.
9.5 Identity Authentication and Agent Authorization. Securely manage identity at runtime. Use robust authentication per agent session, GWTs, MTLS, HMAC-based. Assign unique ephemeral session contexts. Combine role-based access control, RBAC, for broad categories, e.g. research agent, with fine-grained capability tokens for specific actions. CG can use doc search but not send command. 9.6 Optional cloud-specific hardening. If you're running in AWS, GCP, or Azure, leverage their specific features. Restrict access to the instance metadata service. Use Cloud IAM rules scoped tightly per vMagent. Explore confidential computing options if available for hardware-level memory encryption.
What an incredibly thorough roadmap for runtime security. It really paints a picture of multiple overlapping layers of defense, from the hardened OS foundation right up to dynamically controlling the AI's actions and monitoring its behavior in real time. This level of detail feels absolutely necessary for building systems we can actually trust. Hashtag tag tag outro. So there you have it, a really deep dive into securing agentic applications, using the OS-based Securing Agentic Applications Guide as our map. We've journeyed through understanding the core components, the agent's brain, its memory, its tools, explored the unique threats they face, and then walked through a complete lifecycle approach to embedding security, from the initial design right through to hardening the runtime environment.
Yeah, we've seen just how critical it is to consider every single aspect. Hardening system prompts, validating all inputs and outputs, rigorously sandboxing code execution, applying least privilege everywhere, using advanced red teaming, implementing robust monitoring and logging. The list goes on. I think the biggest takeaway is that security for these autonomous systems isn't just a feature you can bolt on later. It has to be a fundamental design principle, requiring continuous vigilance, adaptation, and a deep understanding of how these complex components interact. It's really a paradigm shift for developers and security pros.
Absolutely. This deep dive, while highlighting the complexity, also shows how a structured guide like OWASP's can make it manageable. It provides that clarity and those actionable steps, but it definitely leaves us with some big questions to ponder, doesn't it? As these agentic systems become more decentralized, more collaborative, maybe even self-evolving, what new forms of interaction and what new kinds of systemic risks will emerge? How do we prepare our security thinking for intelligences that are frankly still surprising us? How do we future-proof our security mindset?
That's a critical thought, isn't it? The foundational principles we discussed, least privilege, defense in depth, continuous monitoring, secure identity, they'll remain crucial. But how we apply them, the specific controls and architectures we need, will have to constantly evolve alongside the agents themselves. It's going to be a fascinating and challenging journey.
Indeed. If this topic has grabbed your interest as much as ours, we strongly recommend checking out the full OS Gen AI security project resources online for even more detail. Thank you so much for joining us on this enlightening deep dive today. We look forward to exploring more fascinating topics with you next time.